Don't have time. Because 4.3 is a really long section. Also, I'm hoping to get to the first part of 4.3 today. If we do, if you check the homework like right before class, there's a 4.3 part 1. So I'm splitting the homework into 2 parts because it's another one like the functions where there's lots of stuff. But unlike the functions where there was lots of stuff, but it was all just functions, 4.3 is prime number theory and then greatest common divisor and LCM theory. Like it should be 2 sections in my opinion anyway. So I'm breaking it into 2 separate homeworks. I mean, it's the same number of problems that would have been 1 homework. So it's not that big of a deal. It's just allowing you to like see the distinction, have different view aids, don't do them all at once. All right, so we're talking about how to do different bases. We mainly are going to focus on binary, octal, and hexadecimal, but you could do all this stuff for any base you want. Like I would expect on the test, a test question, like put it into like base 9 or something. I don't know, just some base we haven't done, just to make sure you're not like memorizing how to do these certain bases, but you don't know how to do them in general. So I'll probably throw something like that on there. So let's do a quick example. Let's say find the binary expansion of 241. Recall, if I write it like this, that means base 10. If I don't explicitly tell you the base, we always assume it's base 10. So let's just start. Remember what we did is successively divide by the base. Binary is base 2. So 241 is equal to 2 times 120 plus 1. And then you divide what was your q by your new p. 120 is equal to 2 times 60 plus 0. Again, just continue the algorithm. 60 equals 2 times 30 plus 0. 30 equals 2 times 15 plus 0. 15 equals 2 times 7 plus 1. 7 equals 2 times 6 plus 1. 6.
2 times 3.
Did I mess up?
2 times 3 plus 1 to 7.
Oh, yeah. 2 times 3. Sorry, I was thinking 6 plus 1. Yeah, 7. 3 times 3 plus 1. 6. 3 is every day.
I think it's the other room. No, I was thinking it's like the other room, like if they press the button.
Maybe they're messing with it. But anyway, 2 times 1 plus 1, and 1 is 2 times 0 plus 1. These numbers aren't terribly important in the long run. They allow us to continue the algorithm, but the numbers we care about are these ones. And again, the reason we care about these, let's look at this. So we have 241 is equal to 2 times 120 plus 1. So that's 2 times 60 plus 1 plus 1, which is 2 squared times 60 plus 2 plus 1. I'm going to say plus 2 to the 1 plus 2 to the 0, just to show what's going to happen here. Then we look at 60. We said we could write 60 as 2 times 30 plus 0 plus 2 to the 1 plus 2 to the 0. So that's 2 cubed times 30 plus 0 times 2 squared plus 2 to the 1 plus 2 to the 0. All right, 30 is 2 times 15. So that's 2 cubed times 2 times 15 plus 0 plus 0 times 2 squared plus 2 to the 1 plus 2 to the 0. So that is 2 to the 4th times 15 plus 0 times 2 cubed plus 0 times 2 squared plus 2 to the 1 plus 2 to the 0. And since this one's not a very long one, I'm actually just going to go through and do the whole thing. 15 is 2 times 7 plus 1. You don't ever need to do this. Like, this is just a justification for why you can just read these numbers off. 2 to the 4 is 2 to the 7 plus 1 plus 0 times 2 cubed plus 0 times 2 squared plus 2 to the 1 plus 2 to the 0, which is 2 to the 5th times 7 plus 2 to the 4th plus 0 times 2 cubed plus 0 times 2 squared plus 2 to the 1 plus 2 to the 0. 2 to the 5th, 7, 2 times 3 plus 1 plus 2 to the 4th plus 0 to the cube plus 0 to the squared plus 2 to the 1 plus 2 to the 0. Alright, so that is 2 to the 5th, 2 to the 3 plus 1, or sorry, 2 to the 6th, lost my chain. So if you've noticed the pattern, I replace, simplify, replace, simplify, replace, simplify. That's what I've been doing. So 2 to the 6th times 3 plus 2 to the 5th plus 2 to the 4th plus 0 times 2 cubed plus 0 times 2 squared plus 2 to the 1 plus 2 to the 0. 2 to the 6, 2 times 1 plus 1 plus 2 to the 5th plus 2 to the 4th plus 0 times 2 cubed plus 0 times 2 squared plus 2 to the 1 plus 2 to the 0. Almost done. 2 to the 7th times 1 plus 2 to the 6th plus 2 to the 5th plus 2 to the 4th plus 0 times 2 cubed plus 0 times 2 squared plus 2 to the 1 plus 2 to the 0. And of course, this is just 2 to the 7 plus 2 to the 1. I'm going to write the 1s in now. 1 times 2 to the 7, 1 times 2 to the 6th, 1 times 2 to the 5th, 1 times 2 to the 4th, plus 0 times 2 cubed, plus 0 times 2 squared, plus 1 times 2 to the 1, plus 1 times 2 to the 0. Alright, so that was fun. But what we learned here is the binary expansion. Because remember, what is a binary or any base expansion? It's the unique way you can represent it by coefficients acting on powers of the base. So if we're in base 2, these are powers of the base. This is the unique way to do it, like by doing these successive divisions and then like building it back up. We've shown that that's how it's done. So that means we can just read these off. So the binary expansion is of 241 is, well, I'm not going to group them. 1, 1, 1, 1. Let's see, there's 7, so there's 8 of these. Oh, that'll actually work out. 1, 1, 1, 1. 0, 0, 1, 1. I'll put this in base 2. Unless I made a mistake somewhere in my arithmetic, nobody called me on it.
Somewhere I feel like you made a mistake.
The second line is.
The second line?
It should be plus. I just realized it too. It should be 2 times 60 plus 0.
God damn it. Well, this is an incorrect example. I'm not doing it again. Of how it would work. This is also an example where if you make a small annoying error in the early lines, it's all garbage. But either way, this was just showing you how it's done, so we're going to read this off. 1, 1, 1, 1, 0, 0, 0, 1. So this, the only difference should be this is 0.
Should be 1, 1, 1, 0, 0, 0.
1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 1. Okay. Because remember, we read these off from the bottom up, and the reason we read them off from the bottom up is what I was showing you. Like that's the math behind, that's the direction we read. So if I had done that right, I would have gotten 1, 1, 1, 1, 0, 0, 0, 1. Make sense? All right, so that's how we do those. I guess I'll do an example of octal and hex because they're pretty quick. So these are the ones I had you guys working on in class last time. Find the octal expansion of 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 is equal to 1, 5, 4, 3. I'll do it the same way as before. 8 times 1543 plus 1. 1543. By the way, we want to calculate for this stuff. Like this one, we're working with 2s, it's pretty easy. But when we're working with like 8s, 7s, or 27s, it gets hard.
So we can use a calculator on the test.
Definitely. Yeah. In fact, you'll be supremely disadvantaged if you don't have one. I.e., you'll probably fail the test. Plus 7. And I won't have a calculator if you borrow me, so remember your calculator. Or bring extra calculators and charge people like $5 for the use of it afterwards. 192 is 24 times 8 plus 0. 24, that's one I can do. 3 times 8 plus 0. And then 3 is equal to 0 times 8 plus 3. So the octal expansion is 30071. Base 8. Okay. And let's do a hex one just because the hex does have that like encoding into letters business going on. The algorithm's the same, but you have to remember like if you get a plus 13 there, that's going to be D. I think it's D. 13 is D. So no, we didn't have to do all this nonsense. Like once it's proven, it's established, we just read it off. So don't do this on the test. It'll take a lot of time that you're not supposed to be spending on that. That's time you're supposed to be spending on other things. Don't do this on the test. You still have to do that work. Let's do a hex example. Find the hexadecimal expansion. Oh, 177,103. Why not? It's a good number. So 177130, you use your calculator. By the way I do this when I'm going through is I do 177130 divided by 16, subtract off the whole number part, then I have the decimal part, I multiply that by 16. That will give you the remainder. You want to get really fluid and quick at doing these, so I would practice these on your calculator to find a method that works good for you to do them quickly. Because on the test, like, speed is going to be key. So just get really well practiced, like have a system that you're going to do to keep generating these. Some people like code it into their calculator. If you go to coding calculators, it's fine, I don't care. You can do that as long as it spits out the numbers. And then you write it as if you did it like this. Some people just are really good with using the previous answer stuff, and they like make a little like loop. They can keep hitting the same button, but or just get really good at typing it all in manually. 177130 equals 11070 times 16 plus 10. 11070 equals 691 times 16 plus 14. 691 equals 43 times 16 plus 3. 43 equals 2 times 16 plus 11. And 2 is equal to 0 times 16 plus 2. So it should be right, unless I was wrong when I was preparing my notes. So we're going to read these off. So we would originally we want to write 2, 11, 3, 14, 10. Of course, that's not hex code. That's what am I looking for? Indeterminate, I guess. Like remember we were saying, like, is this 2, 11, 3, 14, 10, or is it 2, 1, 13, 14, 10? Or that's why we use these symbols. So remember A, B, C, D, E, F is 10, 11, 12, 13, 14, 15. So this is actually 2, B, 3, right? 14, E, 10, A. So 2B, 3, E, A. Base 16. You don't need to write it out like this. I just did that to make a point. Like you can just read off 2B, 3, E, A. You just write A, B, C, D, E, F, and the numbers underneath them. See the association. Does that make sense?